Ladies and gentlemen, today's class recording has started. So, over the past couple of days, we introduced the concept of mechanical energy. So let's start at the end. What is energy? How are we going to define energy as we move forward? Do we want Jack to do it or somebody else want to do it? So, okay. Sammy, go ahead. So, Sammy said the ability to do work, and the reason I don't like to use that is because work has its own definition, so I don't like to use that there. So the ability to do stuff or things or change stuff, right? The ability to make things different than they were before, all right? And then the past couple days, we spent a lot of time talking specifically about mechanical energy. So what is mechanical energy? Well, there's three things that make up mechanical energy. You guys are allowed to look at, like, your notes and stuff from the past couple days. This is not a pop quiz or anything like that, So find mechanical energy. We've only done one outline, so it shouldn't be too hard to find it. All right. So, Jack, go ahead.
It's a combination of kinetic potential with gravity and elastic potential.
All right. So it's the combination of kinetic, gravitational potential, and elastic potential. All right. So kinetic energy is energy based on what? Motion, right? The fact that something is moving, it has the ability to change other things. Gravitation, or let's go with potential energy in general, is energy of what? Shape or position, right? So if kinetic energy is energy of motion, potential energy is energy of position or shape. Gravitational potential energy is energy of position relative to gravity, right? How high up the ground are we? And elastic potential energy depends on the shape of that object. All right? Good there? Good with those things? All right. So that being said, right, let's shift here to conserved quantities. Conservation is one of those foundational ideas that are going to apply to a ton of different areas. Right? We kind of talked about it at the beginning of the year, right? If science looks like a tree, conservation is part of the trunk. It's one of those foundational ideas that all the other branches and limbs of the tree depend on. All right? We introduced the idea of conservation in the last unit. We talked about conservation of momentum. So what does it mean when we say that there is a conservation of momentum or that momentum is conserved? Right, go ahead. It stays the same from beginning to end, right? So regardless of what quantity we're talking about, if it's conserved, it means that it remains constant. If we measured that quantity at the beginning of a situation and then at the end of a situation, what are we going to find? It's the same. That's our definition of conservation. So we have been introduced so far specifically to conservation of momentum. The momentum at the beginning of a situation is equal to the momentum at the end of a situation, right? And we said that we can't just look at one object specifically, we have to look at the big picture, the combination or the system that we're dealing with, where system is multiple objects interacting with one another. Okay? All right. Good with this definition of conservation. All right? So, momentum is a conserved quantity, but energy is also a conserved quantity. Meaning, what's true about energy if we say that it's conserved? It's never lost, right? If we look at the amount of energy at the beginning of a situation and at the end of a situation, what should we see? Should be the same, right? The total amount of energy in a closed system will remain constant. And there's some key words that we have to throw in there, all right? I hope that you can figure out one of the key words that we have to discuss in more detail. What do you think one of them is? Total, right? What tipped you off that it was total? It's in caps, right? So on the very first day of this unit, we talked about all different kinds of energy. So what we'll find is that in certain situations, one kind of energy will transfer into another kind of energy, right? The best, easiest example I can give you of that is this, right? Take your hands, right? Put them together. And rub. Well, friction is not a form of energy. Friction is a force, right? But what is friction doing to energy in this situation? You can't increase energy, right? Energy is conserved. It's creating heat, which is what kind of energy? We remember from the other day? Thermal energy. But what has to happen in order for the amount of heat to go up? What do we first have to do with your hands? Move them. So what kind of energy are we starting with, Eric? We're starting with kinetic energy. And that kinetic energy is turning into thermal energy, right? If you've ever done this before, right? If you slam the brakes on a car or a bike, right? Your bike's moving, you slam the brakes on, you skid to a stop. Afterwards, if you feel the tires, they're going to be really warm. That kinetic energy that you had while your bike was rolling down the street has been converted into thermal energy. How much thermal energy will there be at the end of the situation? The same amount as kinetic energy at the beginning, right? Does that make sense? So when we're talking about total energy, right, all kinds of energy, right? Also, closed system. We kind of introduced this idea when we talked about momentum, right? Closed system means we have to look at the interaction of things. And we have to look at the two objects or more objects as a group, not individually, right? So if we look at a system of objects, we will find that individually, one type of energy might go up and another type of energy might go down, but when we look at the total, we're going to find it's the same, right? In this situation, or the skidding wheels across the ground situation, kinetic energy decreases, but thermal energy increases to keep the total the same. Does that make sense? Good with those ideas? All right. Now, it's hard for us in our everyday situation to sometimes show the conservation of energy because it's hard for us to measure the thermal energy that increases when we rub our hands together, or the thermal energy that increases when your bike skids to a stop. But under certain conditions, this conservation of energy is applied to a more specific situation. And that situation, we already talked about mechanical energy, right? Is conservation of mechanical energy. All right? Conservation of mechanical energy. So here's what I want you to do before we get into this definition. All right? Either at the top of your page or along the side or something like that, I want you to talk to the person next to you or in front of you, behind you, whatever, and see if you can come up with a mathematical expression that represents conservation of mechanical energy. A mathematical expression that represents conservation of mechanical energy. Talk to the person next to you. Go.
Is that what you want?
I want you to come up with a mathematical expression that represents conservation of mechanical energy. Knowing what you know, how about this? Knowing what you know about the four words up at the top of the board right now, come up with an equation that represents that. Knowing what you know about these four words, of is pretty easy, so that, this breaks down to 3 words, right?
Maybe a Frank compared to gas.
All right. Are we ready to discuss? 10 more seconds. Go ahead, keep talking if you're still talking. Actually, if there's anything we're going to get picky about it, Frank's is actually a little more right than Jack's is. So, a little. All right, are we ready? Okay, so, like I said, based on the 4 words up at the top, right? Well, here, let's get your answers, and then we'll talk about, right? So, he said, well, sorry. This is what it means, right? Okay, mechanical energy is conserved. Now, there's one condition that we have to put on that when there are only conservative forces. We haven't introduced the idea of conservative forces yet. We'll get that in a second, all right? But when there are only conservative forces acting on an object, mechanical energy is conserved. All right? Good there? So, let's talk about your expressions. I hope that all of your mathematical expressions, regardless of how you wrote them, included this. Yes? Right? It's an equation. A mathematical expression, right? What? How about this? How about this? I'm being 100% serious. I was not aware that that was the case. So, how about this? A mathematical representation. How is that? Okay. So, if we're talking about conservation, this has to be part of our mathematical representation, right? Okay. So, Jack, can I start with yours? Because you guys saw it first, right? So, Jack wrote this. Okay? Anybody else come up with this? So, this is pretty good. There's one thing that I might throw in there. Okay? I might include this. Right? Okay? So, that's one way that we can mathematically represent the conservation of mechanical energy. Alright? Frank, can I put your expression up on the board? Alright? So, Frank did this. Okay? This is what Frank wrote. How's that? That's conservation of mechanical energy too, right? All Frank did was make a more detailed version of what mechanical energy is, or the things that represent, or the things that make up mechanical energy. Actually, the one that's on the bottom, we're going to use when we do calculations because it is a little more detailed and we can talk about those little pieces. But do we understand that this is how we mathematically represent conservation of mechanical energy, right? Because that's what it means, right? The mechanical energy is the sum of these 3 things. And we either represent it this way or we represent it that way, right? One's just more detailed than the other one, but they mean the same thing, right? So, let's go here, right? Okay. So, when there are only conservative forces acting on an object, okay, mechanical energy is conserved, and that can be represented in one of these 2 ways. And that should be, there it is, it's on your outline, letter C number 3 down at the bottom. It's already written out for you, because that takes a long time to write out, as you can see. All right? So, both of those are there, okay? But there's this piece that's included in here that was included before, that piece about the conservative forces, all right? Yesterday, we introduced the idea of work. What was our definition of work? can lift your outlet. Oh, good.
Moving an object.
That's how we do work. What is our definition of work? The transfer of energy. And that means, Olivia, if we're doing work, what has to happen to the energy of an object? Increase, or we also saw a situation where it could also, if it could increase, but it could also do what? It could decrease as well, right? But it has to be different than what we started with, right? Alec, we said that the only way, like if we took this baseball as an example, right? The only way we're going to increase its energy is we have to do what to it? We have to move it, and in order to move it, we have to apply a force, right? So, forces are required for work. But what we'll see is not all forces behave or cause the same kind of work. Alright? If I throw this baseball, I apply a force to the baseball, I move the baseball, the kinetic energy of this baseball has to increase. Based on what we talked about previously in this period, what should we also see somewhere else? If kinetic energy of the baseball increases, what else should happen? Something should decrease, right? Because that leads us to what, Sammy? And our fancy name for that is conservation, right? So, when I throw the baseball's energy increases, but my energy decreases, right? I get a little more tired, right? Now, throwing a baseball one time obviously doesn't give me that much tired, right? But if I keep doing it, I continue to put energy into the baseball's energy keeps going up, my energy keeps going down, we're conserved, all right? So, my energy goes down, baseball's energy goes up, right? But what we find out, that taking into account, right, that key word from the first slide, total energy, right? This is kinetic energy, mechanical energy, but my energy is chemical energy, my breakfast that I had this morning, right? Yogurt with granola in it. That's what I had for breakfast this morning. So, no, it was just plain Dannon vanilla. So, I'm not a big fan of Greek yogurt. I keep trying it because I'm like, it's supposed to be good for you. And every time I try it, I'm like, I don't like this. You know what else that happens with me? Salmon. A lot of people. My wife loves salmon, and I've tried it like 3 or 4 times, and I'm just like, I don't like this. Like I know it's supposed to be delicious and good for you, and I want to try it, but it just doesn't work for me. Right? So, very good. The place I used to work before I became a teacher, we actually we made fruit products. So like fruit on the bottom yogurt. We made the fruit on the bottom yogurt, which is basically it's basically jelly. It's basically jam. That's all it is. Right? Yeah. But some of the ladies that worked there, they would make yogurts. We'd have to like test it and stuff like that. So, yeah, it's kind of an involved process, but it's kind of cool. But yeah. Do you like your grandma's homemade yogurt better than like this one? Does she load it up with like sugar and stuff, or she just goes like straight up milk? I don't like plain yogurt. Like I need to have sugar in my yogurt. I love key lime pie. So. Key lime pie is pretty good. So. Like do you like key lime pie like in its key lime pie form, or do you just like it as yogurt? Oh, okay. Like have you ever had key lime pie? Okay. I mean, I like key lime pie. I like key lime pie yogurt too, but I like
yogurt or yogurt plate time.
So.
Those ones that like root or whatever lactose It's like the whipped kind.
Oh, the whipped kind. The whipped kind is kind of a ripoff. Because they're just selling you air. Like it costs the same as the regular yogurt, but it doesn't fill you up nearly as much. So. All right. I don't even remember how we got there, but whatever. So. We talked about my breakfast this morning. So that's all right. But what we will find is that with certain forces, backtrack that conversation. Energy was conserved, but I turned chemical energy from yogurt and granola into kinetic energy of the baseball. But under certain circumstances, we can turn one form of mechanical energy into another form of mechanical energy, but only certain forces do that. And so, we refer to those forces as conservative forces. Conservative forces, this is a little bit earlier in your outline. So, Roman numeral 2, letter B, should say, when there are only conservative forces acting on an object, mechanical energy is conserved. And so then, Roman numeral 2, letter C, says conservative forces do not change the amount of mechanical energy in a system. But there's only two conservative forces that we will encounter. Gravity, and then elastic forces, like springs and rubber bands and stuff like that. Right? So when we have one of those two forces, or both of those two forces, we convert one form of mechanical energy into another form. So letter C, number 1, A and B. A is gravity and then B is elastic force, so that's why there's two spots there. So. If you got it both written on A, that's fine. But more importantly, conservative forces will convert one form of mechanical energy into another, but the total amount of mechanical energy remains the same. So we don't see this conservation of mechanical energy in all situations, only if one of these forces is responsible. So, because these are forces, do they do work on an object? Yes, but what we'll see is that the work that these forces do doesn't change the total amount of energy. It converts one form of energy into another form of energy. Okay? Good with this so far? Alright, let's talk about the most basic situation that represents conservative forces. Alright? You guys have this picture on the right-hand side. Okay? So, terrible situation, right? Buildings on fire. This lady trapped in the top of the building, flames closing in, right? She has concluded that her only option is to jump out of the window, all right? So, she gets to the edge, contemplates a little bit, but she realizes this is her only chance to survive, so she steps off the edge. Dramatic moment, and just very good. So, at the instant, well, you can see from your picture that there is some. At the instant that she leaves the ledge, what is her instantaneous velocity? 0. Right? The moment that she steps off the edge, just like the moment that I let the baseball go, it's not going anywhere. As a result, what do we see about the kinetic energy that this picture has listed at that moment in time? 0. It's not moving. But she is up in the air. So it has a certain amount of potential energy. Now, we don't know what her mass is or how high this building is, but if we put those two things together with the acceleration of gravity, it comes out as 10,000 joules. All right. The instantaneous velocity is 0 right when she steps off the edge, but what starts happening immediately? Acceleration. Oh, the big wall, but it's not that big. I don't know. They're rolling marbles on a ramp, so maybe the marbles are rolling.
Yeah, going to be on.
No.
Yeah.
We're We're mature. All right, so the instantaneous velocity is 0 when she steps off the edge. But like we've talked about, even though the velocity is 0, there's still acceleration. So she starts falling. And what happens to her velocity as she's falling? It increases, right? That's going to do what to the amount of kinetic energy that she has? It's going to increase her kinetic energy. But the increase in velocity is accompanied with a decrease in height, right? She's falling. So as she's going faster and faster and faster, increasing her kinetic energy, what's happening to the potential energy? It's going down. So halfway down, right, we see that the potential energy has been cut in half. 10,000 joules of potential energy is down to 5,000 joules. But the kinetic energy has increased. Total amount of energy is equal to what still? 10,000. So this is where the conservative force thing gets a little tricky. Was there a force applied to this woman? Gravity. Gravity's force, right? Did she move because of that force? Yes. So that fits the definition of work, or the calculation of work, right? But Olivia, you said that before, work causes the energy to do what? Increase or decrease. Has her energy actually increased or decreased? The total is the same. What makes conservative forces special is that they don't change the total amount of energy, but they convert one form of energy into another form of energy. Does that make sense? Within that same object. As she continues to fall, right? Kinetic energy continues to increase as she goes faster and faster and faster and faster until she reaches the bottom, right? Where at that 0 height, the ground, or wherever we call the bottom of this fall, she has no potential energy because her height is 0, but she has made up for that decrease in potential energy with an increase in kinetic energy. Is mechanical energy conserved in this situation? Yes. One mechanical energy went down, the other mechanical energy went up. Alright? So, Roman numeral 2, letter C, number 3. There's a little question. Is mechanical energy conserved in this situation? Why or why not? So, in order to answer that question, first you have to answer the first question. Is mechanical energy conserved in this situation? Yes. Why? Well, what does it mean for mechanical energy to be conserved? The total of kinetic and potential gravity and potential elastic, the total of those three has to equal the final total. And we see that here in this picture. Right? So, one more thing before, okay, sorry, finish writing that down and we'll do the last picture here. Just to the right of the picture of the lady falling down, there is a graph. And that graph is titled Conservation of Mechanical Energy in Falling Objects. And there's an x-axis and a y-axis. X-axis is labeled time, y-axis is labeled energy. Alright? So, let's draw 3 lines on that graph. If you got 3 colors, that'd be awesome, but if you don't have 3 colors, that's okay. You can just label them. Alright. So, one line is going to, and it's the easiest line you can draw on the graph, one line is going to represent the mechanical energy what would the line representing mechanical energy look like? Eric. A horizontal line across 10,000, right? Do I have this written? No, I don't. So here, let's do this. Let's do this. Let's do this. Alright. So, in this case here, my purple line is going to represent mechanical energy, and that's going to go straight across here. Okay? Alright, second line. And this one is the tricky one, but if you get the tricky one first, then the other one becomes easy. Let's do kinetic energy. Alright? So, we know that kinetic energy is going to have to do what in this situation? Increase. It starts at 0, right? But, here's why this one's a little tricky. What did we learn, what happens to the velocity of this object as it falls? It increases, right? And that causes the kinetic energy to increase. But, going back to a couple days ago, what kind of relationship do kinetic energy and velocity have? No, not direct. Quadratic, right? KE is equal to 1/2 mv squared. What do quadratic relationships look like on graphs? They look like parabolas, or in this case, 1/2 of a parabola. Kinetic energy is going to start down here at 0, because that's what it was at the beginning, and it's going to increase. But it's not a straight line increase, right? It's going to look like this, and go like that. Alright? Does that make sense? So that red line represents our kinetic energy. And then, what do you think the third line is going to represent? Potential. Specifically, what type of potential? Gravitational potential. We know that gravitational potential has to go down, right? But is it going to be a straight decrease? And no, it can't, because what do potential and kinetic have to add up to? They got to add up to 10,000, right? So if this one's only getting a little bit bigger at the beginning, how much does potential energy have to go up? Or sorry, how much does potential energy have to go down? Just a little bit, but mostly the same, right? So here, this is going to have to go like this, right? I might not have hit it perfectly, right? That is what point? The yellow arrow that I just drew across represents what point in the lady's fall? When we're equal, so how far down the building is she? Halfway. Question. Should that point occur halfway from left to right on this graph? The right answer is no. Because, Jack, what is she doing as she's falling? Does it take the same amount of time for her to do the first half of her fall as it does to do the second half of her fall? The second half of her fall, she's going faster. So this is not going to happen halfway from left to right. It's going to occur more towards the end, because the x-axis on this graph is what? Time, not distance. Good, Rick.
So like, when they're equal, it's 5,000, 5,000. Is there like a term like last second or eternal?
No, it's just, that would be the halfway point of this fall. All right? So, real quick, before we get done today, nothing new information-wise, I just have to bring up a point here on this picture, okay? So, this picture here reminds me of two things. One, in old movies, you see this, like, these firemen holding this big thing, right? But nowadays, nobody would do that. They just get a big ladder and, like, you know, like the big fire truck that has the ladder on it, they just, you know, everything. So I wonder if they have that sitting in their attic at the fire station, and they're like, you know, maybe we should keep this just in case one day. right? And every year, everybody at the fire station wants to throw it out except one guy. He's like, no, we have to keep it, right? But two, this picture really reminds me, whenever I use this picture in class, of the best day of elementary school gym class, parachute day, right? Man, when you walk into gym class in elementary school and that parachute's out on the floor, you are like, yes! Best day ever. Sharks and lifeguards. My daughter just played sharks and lifeguards yesterday in gym class. So, all right, everybody. Hey, don't forget the quiz over kinetic potential and work. And we'll continue on with conservation tomorrow.